There are two more sets of handouts up here. Anybody want one? Okay. Did that mean everybody got one? I can't imagine that everybody got one, but okay, if you did. If you didn't, just drop by my secretary's office. She's got more. It's just so many that I could fit on that cart without rearranging it. Actually, those things on the first page actually have some of the evaluations from the early years of the course. And some students say, well, you can get as much or as little as you want out of this class. Depends on how much time you want to put into it. So in there, in the one that says 1, there's a chapter 16, which is something I wrote about 20 years ago for a book that the mechanical engineering department was going to publish, which I don't think they ever got around to publishing, but it's supposed to be on manufacturing, I guess, was the topic. And basically I just took all my lecture notes home on the welding and joining stuff, and I condensed everything down to about 30 pages. So if you want to learn everything about the 25 lectures, you can just read those 30 pages. At the back of that chapter 16 are 10 problems, which would be the problem set that you could do for your assignment. MIT requires me to grade an assignment in order to give a grade. So that's why you have an assignment in this course. If I didn't have to give you an assignment, I wouldn't, okay? But it's up to you. Some of these references are getting kind of long in the tooth, but they're still general things, and for whatever it's worth, you can decide to read them or not. Some people try to read them all, which I wouldn't do that. There's a copy of my World Trade Center paper. We'll probably talk about that at some point. I'll bring it in at some point, probably on how to communicate. But that, for a long time, was the most referenced article on the World Trade Center collapse. Okay, I was #1 on Google. I think I'm #2 now. But anyway, and there's all the conspiracy theorists hate me, okay? Because I explained it. But anyway, in fact, the BBC is doing a documentary, and next Thursday, I think, not this Thursday, but next Thursday, I'll be down in the Washington area, and they want me to meet with them on some stuff because they're doing a documentary on the World Trade Center. But anyway, by the way, it was the airplanes. It wasn't a government conspiracy. Okay. Although my favorite, well, I'll tell you some of my favorite stories on those things later. It's amazing what people can believe. But anyway, what else did I want to tell you? So that's, my favorite evaluation of all time is the student who said he just wanted to know what I taught at lunchtime, because I got breakfast, right? He just wanted to know, what other course he could take at lunchtime to get a free lunch. So anyway, okay, a number of things to clean up from last time. I finally found, it was in my thing here of notes, but the properties of MP35N. Let's brighten that up a little bit. So here's the typical room temperature tensile properties of MP35N. It's a function of the amount of cold work. So the yield strength when in a completely annealed condition is only 60 KSI. That's nothing to write home about. It's low strength steel is 36 KSI. It's not hard to get 100 KSI steel. 60 KSI is sort of in between, but it can go up to 235 KSI with 65% cold work. And if you do a heat treatment on it, an aging treatment, you can get it up to 290 KSI, 300 KSI tensile strength. Now this is better than most aircraft landing gears, which are kind of the epitome of high strength steel, okay? So this is better than that 10% elongation and 48% reduction in area. That's pretty incredible, okay? To get that much stretch out of something that's that strong. The problem is you can't make it in really big sections because it has to be cold worked. And what are you going to cold work it with? Once it starts getting up to these strengths, all the other tools are just going to break, right? Yeah.
What do you mean by cold work?
Cold work is deforming it and shaping it at room temperature, okay? However, room temperature is a relative thing. For tungsten, room temperature is 2,000 degrees, okay? It's the temperature at which the material does not self-anneal, okay? At higher temperatures, the material will, if you're interested in material science, the dislocations will annihilate themselves. But with cold work, you're at a low enough temperature that if you deform the metal, you form these tangles of dislocations and they stay there. And they actually make it stronger, okay? But if you're not a material scientist, you don't even know what a dislocation in a crystal is, right? So, okay, but I mean, basically, cold work is working at a temperature such that the material doesn't annihilate the dislocations and self-anneal, doesn't recrystallize. It maintains the deformed microstructure on an atomic scale. And all materials will cold work. The cold working temperature for lead is below room temperature, okay? The cold working temperature for steel is actually around 400 or 500 degrees Fahrenheit. Anything below that temperature, it doesn't stress relieve itself, okay? For tungsten, it's even higher. But for MP35N, it's probably the 300 or 400 degree Fahrenheit range. It doesn't soften while you're working it. It just gets harder and harder and harder. In fact, actually, if you look at the stress strain curve, so if you've got stress and strain, and you come up here to yield strength, and it just keeps going and going and going, anything above the yield strength, if it maintains its strength, you've worked it to that strength level, okay? But what happens is if you heat it up, it'll come back down. If you anneal it, it'll come back down and it would yield again at a lower temperature if you've heated it to the high temperature. Things like a blacksmith's forge, when the steel gets red hot, that stuff is plastic and you can form it, you can put it back in the furnace, heat it up again, and it will soften and you can rehammer it, right? One of the great advantages, in fact, I wrote my junior humanities term paper, not term paper, but assignment on the history of the hardening of steel. The ability to form a material in a soft condition and then strengthen it or harden it is a very important property. How do you make clay pots? You take nice soft clay, you can form it any way you want, then you put it in a furnace, you heat it up and it becomes hard and it becomes a piece of dinnerware or bakeware or whatever, right? If you just had clay, it wouldn't be very useful, soft clay, to bake bread in it or something if it just fell apart, right? Well, steel can, by heat treatment, steel can go from these types of strengths to these types of strength, but not with these types of ductilities, not with this ability to stretch and absorb energy, okay? Ordinarily, as you go higher and higher up on that curve, your ability to absorb energy gets less and less. And for those of you, particularly those of you in the Navy that go underwater, it's very important to have something that has not only strength, but the ability to absorb energy. Because if someone starts exploding things next to you, you want something that doesn't shatter, okay? Like glass. Glass makes great research submarines or deep divables, but it doesn't make a very good something to take undex, okay? All of you know what undex is, underwater explosion, right? So if you could make an MP35N submarine, first of all, if you could afford something 200 times the cost of steel, and if you could get it in thick enough sections, it would be corrosion resistant, it would take explosions with fantastic properties. The problem is you can't make it as in a plate form, you can't make it in diameters much above 2 inches, okay? Because you gotta mechanically form it, and there's no tools in the world. You'd have to cast a great big piece, and there's no tools in the world that wouldn't break in trying to break that thing down to a smaller piece, okay? So there's no tools to form this stuff. except in small diameters and stuff. And in fact, you can get it in wire form or sheet form. Wire form is great because you can pull it through carbide or even diamond dies. So there are materials that are hard enough, but you can't do that with great big plates. Okay, you couldn't pull this material through great big plates. Okay, or great big plates through some die. You don't have the diamonds and you don't have the force to pull it. So anyway, that kind of takes care of that. There are, I don't know if we need to, there are some sort of interesting, we were talking about fasteners. There's one type of fastener that's used very commonly that was a bit of serendipity, and it's called Velcro. Anybody know how Velcro is discovered? Yeah, here's the cockleburr. Okay, so this guy was walking through the Alps somewhere, and he came back and he noticed he had all these cockleburrs on his pants, and he thought, huh, I wonder why they stick to my pants like that. So he put them in a microscope and he noticed the end of each of the cockleburrs has a little hook on it. Okay, and he realized that his wool pants also had all these little loops. Okay, and so he said that might be interesting as a type of adhesive. So he basically took plastics, and he made a bunch of loops, and then he made some little hooks, and that was the invention of Velcro, which is actually sort of an interesting fastener. Okay, so far as that goes. I've given you in the handout of my notes some references to several books. One, this is the best book on bolting that I know of. John Bickford's retired, but he's an MIT mechanical engineer. This is the third edition of his book. We'll go through some of it right now. If you're interested in bolting of bridges and buildings, this book by John Fisher, who was John's still alive, but he's probably well into his 80s now. But he was a civil engineer at Lehigh University, and he basically looked at bolts for bridges and buildings and things like that, and how to put big arrays of bolts on things and stuff. If you start thinking about fastening, what are the advantages of fastening over other joining technologies? It's in the notes, guys.
Quicker than welding.
It's quicker than welding, and it doesn't require all the procedure qualification that you have to do for welding. Okay, welding, you actually have to work out a procedure that works. It's not too hard to figure out the procedure for putting a bolt in a hole and turning the nut, right? You got to put it right torque on or something, but that's about it.
Easier for repair and maintenance.
Much easier for repair and maintenance. It can be disassembled. How do you disassemble a weld? You got to cut it out, grind it out, you know, it's a pain in the neck. So bolting is great for low volume manufacturing. If you only have to make one of a kind or 100 of a kind or something. But somewhere in there at between 10 of a kind and 1,000 of a kind, it becomes cheaper to braze or solder or weld or something. You can amortize the cost of developing the procedure over a lot of parts, whereas if you're only putting one together, bolting's a lot easier to design, okay? But what are the disadvantages? So it's got ease of assembly, low volume. It's also field assembly we talked about yesterday. The disadvantages are its higher cost and high volume, which we kind of the inverse of what we just said. It's very difficult to automate. If you start thinking about the manual dexterity that it takes to put a bolt in a hole and then turn a nut and not turn it too hard or too soft, okay? If you start thinking of how a robot could do that, a robot has to have a range of mechanical force sensitivity that is sort of natural to us, but not natural to a robot, okay? So just the way of, and be able to put it in a hole, okay? Or to recognize that a hole is not perfectly circular or something like that. These are things that we can recognize. you have to realize, and I point this out to people at the stores all the time. NIST did a study a number of years ago and found that the average IQ of a robot is 10. Okay? And that's because robots can't reason. They can't adapt. Okay? And same thing with computers, basically. They don't really have intelligence, the ability to reason and adapt. And so they have a very low IQ. And you know, I used to give talks at General Motors about they were trying to replace all their workforce with robots, and that said something about what management thought about the quality of the workforce. Okay, they were trying to upgrade with robots, right? So they figured that most of their laborers had an IQ of less than 10. Okay, well, they didn't like it. I used to kind of point out maybe it was the management that had an IQ less than 10. Anyway, it's less than full joint strength. I mean, we used to rivet bridges together, but the amount of extra material you had to do when you overlap those things was horrendous. It turns out the first big all-welded project was the Big Inch pipeline in 1930s. It was a 30-inch pipeline from Louisiana to New Jersey. And the reason they welded it, even though welding had not been used for really critical applications, was because if you had riveted something like that, not only would it have taken twice as much, not twice as much, but a substantial increase in the amount of material. But can you imagine all those bolted flanges and joints and stuff and all the leaks they would have had? Okay, I mean, if something's going to fail, it fails at a joint. We talked about the problem, you have to have the right clamp up, it can't be too much or too little. Fatigue, I mean, you put a hole in something, you just increase the stress concentration by a factor of 3, right? So you're going to have fatigue problems. And it's also only really good in either shear or tension. It's not particularly great in compression, it's just kind of holding things in place at that point. But it's not very good in multi-axial loading. If you got some combined loading of shear and tension, well, it's not that easy to design it because a bolt has a strong direction, just like the trunk of a tree has a strong direction and a weak direction. Okay, so bolts tend to have the same type of problem. Okay, they're not good in that multi-axial loading. So there's a host of good points and bad points. The bad points tend to outweigh the good points in most cases. We already looked at some of these things. Let's see. The whole bolting process is actually best analyzed as clamp up and springs, relative stiffnesses between the bolt and the spring. We're not going to go through that, but another problem with bolts, I talked about the plus or minus 30% variation in torque, but what I didn't tell you is when you reuse bolts, the torque, this is the number of times you've tightened up a bolt. And the torque, the preload is supposed to be 46,000 pounds, and the torque to acquire the preload goes down and down and down as the bolt works its way in and smooths out all the rough spots and the friction coefficient goes down and whatnot. It takes less torque to get the same clamp up. And so if you reuse bolts, who knows where you are on this curve? I mean, that's a pretty substantial difference. It's a factor of 2. It's more than 30%. Okay, it's 50%. The other problem with reusing bolts is bolts are often loaded to about 75% of the yield strength. Okay, there's other things in this book that'll talk about that in Bickford's book. But if you do that and then you put some service loads or excursions on top of that 75%, you'll often start to yield the threads. It might be micro yielding, but now things don't fit up quite as well. So typically, you never reuse high strength bolts. They're one-time article use. Who was talking about more grip bolts and propellers? One of you had experience. You probably didn't reuse the more grips, did you? You threw them away after one use, right?
They had brand new ones and they would replace the blades and propellers.
Right, and that's because even though you're measuring stretch and stuff, they've stretched. The thread fit is not what it used to be because you had micro yielding.
Now you said actually totally replace them if you take a bolt out. What about bolt tightness checks? Because they do that
Yeah, but they didn't completely remove it. They
Correct.
just
That's
kind of
what
go
we-
in and retorque.
That's
Yeah.
if you actually remove the bolt and freeze it.
Right. So when you take it all the way out, and it's not just propellers, it's aircraft, it's bridges and buildings. When you're using high strength bolts, the rule, and automobiles, racing cars and stuff, high strength bolts are one-time use. Now most people don't know that, but I've been to a number of aviation accidents where people reuse the bolts. Okay? They don't have the same fatigue strength because they don't have the same clamp up. So the long-term properties are not the same when you reuse high-strength bolts. Not everybody understands that.
Clamp up
Is the spring force where I showed you we call it clamp up. You torque it to, let's say, 75% of yield. And because it's competing springs, you can think of the two plates you're bolting together as having a certain springiness, a spring constant. You can think of the bolt as having a spring constant. One of them's in tension, one of them's in compression, but they're not the same spring constant, K, okay? Different values of K. If you want to analyze how the bolted joint behaves, you analyze it as coupled springs in parallel, okay? So a 10% variation in the stress on the bolt could be a 50% variation on the plate, or vice versa, depending on the variations in the spring constant. You have to worry about both displacement and force in parallel springs. Okay, again, force is minus kx, right, for a spring. Remember that? Okay, or energy is 1/2 kx squared. Okay, well, the bolt has a value of K, and the plate, or whatever you're bolting together, has a value of K. But those two K values are different. And now you have these two springs acting in parallel. And you got to work out the math for these coupled equations for energy and force. And a small variation in one can be a big variation in the other. Okay? Yep.
What's the fundamental difference with the stud that you pull fasten on?
Oh, well, first of all, that stud is not typically loaded to 75%. It's loaded to 25% or something. I mean, when I'm talking high strength bolts, I'm talking about bolts that are going to be loaded to like 75% of yield. Okay? And those are critical applications, high strength applications. Low strength applications like studs, it's usually just for placing things on. Let's face it, on a submarine you got a million studs, but it's just hanging stuff off the side, right? Just hangers, right? And we can't talk what we're hanging, right? Okay. Okay, so that kind of gives you a little bit on bolting. And there are some in the notes there are some references. So if you ever need to go back to things, I mean, I use Bickford's book about once a month. Now when you go to the lectures that are going to be on video, and I think you ought to start with the material selections lectures. There's like 12 to 15 of those. It'll fit in, mesh a little bit better. But I talk about the variations in the cost of a material. And in fact, if we think this course is really supposed to be about how to manufacture structural materials, and structural materials differ from other materials that the Japanese call them structural and functional materials. Functional materials we are using because of some property other than mechanical properties. Structural materials, let's face it, you're talking about structure, you're talking about mechanical properties, right? And we have MP35N, the wonderful metal of all, greatest metal of all. But structural materials are, by their very nature, are used in very large volumes. You can't build a nano bridge. It doesn't go all the way across the river. Okay, it's not very useful if it doesn't make it all the way across. Okay, the stiffness of anything is going to be proportional to its cross-sectional area and its modulus. And we only have so much to play with in the world because the Young's modulus is determined by the strength of the chemical bond. And steel and cobalt alloys and nickel alloys are all around 30 million, But the best you can get is molybdenum and tungsten and carbon at around 60 million. So you can only get a factor of 2 in stiffness above steel. Aluminum is 10 million, so it's 3 times less than steel, which creates some problems when you're trying to design. Okay, one of the problems with the Visby, you know what the Visby is? It's the Swedish all-aluminum ship or composite ship or whatever. The Visby was this corvette that the Swedes built that was, you know, most innovative or whatever ship of its time about 10 or 15 years ago. But the Visby has problems with hogging and other things, if you know what hogging is. You know, basically a beam between the waves, right? In heavy seas, the ship just becomes a beam between the waves. Well, composites and aluminum just don't have the stiffness to make big long bridges between 2 waves, okay? And so in heavy seas, they tend to break in 2, okay? Not good, okay? So there's a whole range of the cost of these things, and the value of a pound saved in something like a ship or a railroad car is about 20 cents over the life of the vehicle. And this is actually on some of the lectures that you're going to get. It's also in a handout for today that I'll give you right now. This is an article that I wrote when I was on a committee, and it was a little bit of a problem being on this committee because everybody was interested in nanotechnology and all this other stuff. And so we were all supposed to be writing part of this report, and I decided I couldn't write any of this report because I didn't believe in what they were talking about. So I wrote a chapter which they made an appendix, okay? But this is sort of a summary of Tom Eager's feelings about, another person on the back row, about the some of the high-level strategic view of structural materials. There is a plot in here which I stole from Jack Westbrook, an MIT grad. He did this in something like the 1960s for General Electric when he worked there. But this is pounds per year versus dollars per pound for structural materials, okay? And there's a correlation. The less something costs, the more you'll use it. Duh, okay? But the interesting thing is slope here is greater than the ISO market size. So if you can reduce the factor of cost by a factor of 2 in the long run, you'll increase the consumption by a factor of 4 and double your market. Okay, that's the long-term view, okay? In any case, the material we use in the greatest volume is crushed rock, okay? And it has a very low value. Now this is old numbers, so maybe it's rather than 1/10 of a cent a pound, maybe crushed rock is 2 cents a pound now, whatever it is, it's still pretty cheap, okay? The problem with something like that is you can't afford to transport it very far. Who's going to be shipping tons of crushed rocks from China to the United States? It doesn't make any sense. Cement, the largest volume of manufactured material in the world, 2 billion tons a year of cement. And in fact, we can ship cement around the world if you're really going to use slave labor and cheap energy to produce it, okay? But in general, cement plants dot the country because you can't ship it by truck or by rail more than about 500 to 1,000 miles, okay? My father worked for a cement company, and one of the big innovations for one of the cement companies he worked with is they had one big plant in Ravenna, New York, and they had supply depots all up and down the Atlantic coast, and they barged it to each one of these supply depots. So the reason I lived in Virginia Beach was my father worked in Chesapeake, Virginia, where they had a supply depot, okay? Cement was made in New York. barge to Chesapeake, Virginia, and then run by truck for a couple hundred miles all through North Carolina and Virginia. And they had another one, I think, in Baltimore, Maryland or something, you know, or Philadelphia or something. So transportation costs are very important when you get to materials down here. Up here, there's a structural material. It's called diamond. Now, it's not used in very large volumes. I actually have some diamond here. This is a little diamond made by Kinnick, and it's brazed diamonds on a, that's actually just a manufacturer's toy, advertising toy. But here's Kinnick makes what's called a pad conditioner. Okay, this is sort of a functional material. Diamond's a structural material, but it's fairly pricey, and it can't be made in large size. It could be made, they made it in 1 or 2 millimeter thick sheets, very expensive, as a semiconductor substrate, because it has some of the best thermal properties in the world. It can conduct heat away from that semiconductor better than anything else. It's not really being used as structural material there. For a diamond pad conditioner or a diamond sharpener or something, it is being used as structural material. It can abrade other materials better than anything else. The pad conditioner is, have you ever seen someone describe the buildup of a semiconductor? You lay down some copper on the surface or aluminum, and then you'll put something else on top of that, and you'll put something else on top of that, and after a while the thing looks like the Rocky Mountains on a microscopic scale. Every now and then you have to come along, you have to do what they call planarize the surface, and you come along with an abrasive, a chemical and mechanical abrasive, to flatten off the semiconductor before you continue to put more layers on there. Modern semiconductors take 200 to 400 processing steps to make the semiconductor. Individual steps of lay something down, take something off, oxidize something, put something else down in all these different patterns, okay? And there's 200 to 400 steps. That's why that little semiconductor with all those little, somewhere around here, I got a semiconductor we'll pass around. With all those little things that you can't see except with a microscope. Now this is a 15-year-old Intel chip. That's a Pentium 5 chip. But you can see the semiconductors on there. And they have to, as they get smaller and smaller, they have to come along and abrade the surface. And the pad conditioner is basically a diamond that comes in every now and then and gets all the gunk off the pad abrasive that's polishing this thing, because you got to have a good smooth, when you're dealing with microns and submicron polishing, you have to have a nice perfectly planar surface, and so you have to dress your polishing wheel, and the diamond pad conditioner is the thing that dresses the polishing wheel. So these little diamond conditioners are sort of interesting in that way. Anyway, the highest value structural materials are worth about $20,000 a pound. They go into, you might know what they go into? Spacecraft. The value of a pound saved on the space shuttle is $20,000 a pound, because that's what it costs you to get a pound in orbit. And so now they say, oh, we're going to colonize the moon. Yeah, and at $20,000 a pound, how much do you weigh? Okay, how much will it cost to get you to the moon, along with all the food and water and, you know, that you're going to need, right? The International Space Station, those people are costing us $20,000 a pound. Okay, and look at what we've benefited from it. Look at the cost-benefit ratio there. Anyway, this is, pardon me? We got Tang? Yeah, well, not from the International Space Station. Yeah.
The most expensive pictures ever.
I don't know. I think GPS actually has paid for itself in lots of other ways, commercial ways.
So that's just low for 20,000.
Yeah, going to the moon and stuff is probably higher than that. But I mean, that's an order of magnitude number, okay? The original goal of the space shuttle was to get the cost from back in the 1970s, it was $10,000 a pound. I've added a little for inflation, right? They were supposed to drop the cost of putting satellites in orbit from $10,000 a pound to the space shuttle was supposed to get it down to $1,000 a pound. But that was if we had 1 to 200 shuttle flights per year. I don't think we got anywhere close to that, right? So the actual cost of the space shuttle may have been slightly more than single rocket shots, okay? But they didn't know that when they started. But let's not get into the space shuttle right now. It's depressing for me as a taxpayer. This is a piece of HY80 made by our friends down there in Groton. You'll feel the weight and density. That, as fabricated, is probably $2 or $3 a pound for the cost of the fabricated, what you're going to float or sink, as the case may be. That is a piece of the X-33 space plane. That cost $12,000 a pound for that composite. Okay? So you've got $2 a pound and you got $12,000 a pound. Okay? But it's light, isn't it? It's not as strong and it's more brittle. It wouldn't do well in an explosion, but you can get things into space and still have some payload left over. Okay? And you can afford it at $12,000 a pound. But you can't make, you could make an Indianapolis racer out of that material. Okay? But you can't make a Ford Taurus out of that material and sell it to anybody normal. Okay? So anyway, that's part. I'm kind of getting into some of the stuff that's already on the other things. But anyway, so you can, this actually that I just gave you is probably in those big thick packets I just gave you earlier here. But anyway, for whatever that's worth, you now know something about the cost of materials, which can vary widely over about 5 orders of magnitude. Okay? Yeah.
What distinguishes that from
that is a honeycomb. That's the story of the X-33 space plane is sort of a after the first Gulf War. See, I like questions. It causes me to digress. After the first Gulf War, the Defense Department really felt this great need for what they called rapid prototyping. We were developing things like 3D printing and other things. And they found in the war didn't last 5 or 6 years, okay? And so they actually found they needed things and they needed to be able to develop them within 2 weeks or a month rather than 3 or 4 years. So they decided that they would do the X-30. NASA let a contract for $1.3 billion. And if I remember correctly, it was supposed to be 33 months from let of contract to first flight. Okay? And they spent the first part of their Pareto chart, was it Pareto chart? Gantt chart? Which one is the time chart? Gantt. The Gantt chart. Okay, so they spent the first part of their Gantt chart trying to make carbon-carbon composites, 3D composites. Now, if you want to see a piece of carbon-carbon material, just happen to have one here. That's a piece of carbon-carbon material, composite. That was made for chemical reasons. As a tube, it was going to be a filter because carbon has fantastic corrosion resistance in all kinds of acids and other chemicals. And so if you wanted to retrieve your catalyst in a chemical plant from your spent catalyst, which might be made out of rhodium or platinum or iridium or something, you could have filtered it through that catalyst or that carbon-carbon composite. In any case, for the X-33 space plane, they were going to make it out of woven 3D. It was going to be a ring-stiffened cylinder. You guys in the Navy, underwater Navy, know what a ring-stiffened cylinder is, right? But then they priced it out, and they found it was going to blow the budget by factors of 4 or 5 or something. So they decided they couldn't do it. So they were left with about 1 month to go to finish the design. They had spent about 6 months designing this thing they couldn't afford. No one bothered to check the price early on. So they had to slap something together in 1 month. And so you could buy that honeycomb that's not Kevlar, it's well, the firefighters wear. It's the same thing as Nomex composite. It's the same as Kevlar, it's just, anyway, it's called Nomex. It's very similar, plastic, polymer. And they could buy that, and then they could buy tape, graphite tape, not graphite, but carbon fiber tape in a polymer resin, and they could make these. They spent about 30 million of the 50 million on all these fixtures, and then they had to, so they wound up all these things, and without getting into all the details, they made this thing about the size of a 2-story house. It only weighed 2,000 pounds, even though it had Inconel inserts for the fasteners and support struts and things. And they took it down to Huntsville and they filled it up with liquid hydrogen, and that's the only place you can get 5,000 gallons of liquid hydrogen. Okay, not everybody has that. Okay, tends to be explosive. Okay, and so they made 2 of these, and they had just finished doing it. It was successful, and I won't tell you about all the other mistakes going along the way. And they were giving each other high fives, and then the video camera, they saw all the frost pop off, and it turns out they had sprung a leak. And it turns out no one had checked the permeability of the carbon-carbon composite for liquid or gaseous hydrogen. Now, actually, someone at Michaud Division, NASA's research labs down there in Louisiana, had given them some numbers. Well, this gets into the politics of the whole thing. They'd given the contract to the Lockheed Martin Skunk Works in Palmdale, California, where they built the F-111 fighter, you know, the stealth fighter in secret. In fact, that tank was built in the same hangar, the top secret hangar where they built the F-111. Okay, it was the production facility for F-111 fighters, and so NASA, to do this rapid prototyping, they knew that regular old defense contractors could never do something quickly or within budget. So they gave it to the this $1.3 billion contract to the Lockheed Martin Skunk Works, and they were the ones who spent the first 4 or 5 months of their 6-month budget designing something that couldn't be, was unaffordable, right? And so they slapped together this other design in 1 month, built it, had a few problems in the fabrication, and then tested it and had a big problem. Eventually NASA canceled the whole project, okay? But that was supposed to be the replacement for the space shuttle. The X-33 space plane was supposed to be the replacement for the shuttle. But, you know, if you want a liquid hydrogen tank, twice the size of this room, you know, or actually bigger than that, about the size of a small 2-story house, they got one in Palmdale you can get it cheap, okay? I've seen it sitting right there. No one knows what to do with it. Only cost them $50 million a piece for the 2 of them, okay? But 2,000 pounds, you know, divided into $50 million, you can figure the price, anyway, whatever.
So, were you the empty?
Pardon me?
That was the empty weight of the...
That's the empty weight, yep.
How much developed in liquid hydrogen?
Oh, I don't know exactly, but one of the ways to be able to make single-stage to orbit spacecraft was that was what the space shuttle was supposed to be in the original design and concept in the 1970s. It was supposed to be single-stage to orbit, and they found they couldn't do it. They had to have these big tanks on solid rockets and big tanks on the side underneath it that were expendable, basically, sort of reusable, but not that reusable. But they had decided that X-33 is supposed to be single-stage to orbit, so that means you could take it up, bring it back, refuel it, you know, take off like an airplane, right? And you don't have to throw away the external tanks and stuff. And if you could have done that, you might have gotten the price down from $20,000 to $1,000 or $2,000, and so it would have been a game changer for putting things in space. They're still trying to figure out how to do that. But in order to do that, you have to have multifunction materials. So it turns out the tanks were also supposed to be the structural part. They not only had to do the functional, they had to hold liquid hydrogen, but they also had to provide the mechanical properties for the whole structure. And this is actually in one of my other talks. I'll give you more on it. I didn't bring the pictures of the X-33 and stuff. But it's one of these, it's amazing what these little groups in the Pentagon can come up with for ideas, okay? When you have no constraints and you're not constrained by any science or physics. You just say, oh, wouldn't it be great if Buck Rogers could communicate by mental telepathy, right? And so they'll have someone, oh, let's spend $100 million on studying mental telepathy, and that way we'll really improve our C4I or C3I or whatever you call it, right? C5I? Sorry, oh, boy, those C's proliferate. Anyway, pardon me?
It's like C5ISR.
Oh, okay. See, well, they got whole teams thinking of these acronyms, right? I mean, gee, it's just fantastic. In any case, I really am not getting through very quick today, but that's okay. Some of the stories are better than what I have to talk about. Anyway, let's talk a little bit about, well, we have been talking about the difference between structural materials and functional materials. And actually, for the rest of this, maybe that's what I'll do. Actually, maybe I'll go back to my outline. This I didn't hand out to you, so Aaron, you're going to have to type this up, I guess. Materials processing is energy interacting with matter. You can't change the shape or the composition or anything of something without doing something to it. And that means you have to input energy. Now, there are a number of different types of energy. There's thermal energy, and Wolfgang Pauli gave an interesting definition of thermal energy. Heat is a disordered form of energy, okay? Heat is atoms vibrating in all kinds of random directions. Work is basically the atoms pushing all in some uniform manner. In fact, some people talk about work is the atoms in a military formation, okay, all going in the same direction. Whereas heat is a political formation, everybody going in their own direction, right? And later on in the notes, when you get to non-destructive testing, I basically use the same definition for non-destructive testing is energy interacting with matter. You can't measure something unless you do something, probe it with something, some form of energy. And in fact, if you want to get to basic physics, that's the uncertainty principle, okay? There's a certain minimum amount of energy that you have to put into something. Well, there's lots of different types of energy. There's thermal energy. We do heat treatments. There's mechanical energy. We do mechanical forming. There's electrical energy, chemical energy, and nuclear energy. Now, the reason I blocked these off like this is these four happen to be 4 of the 8 departments in the School of Engineering at MIT, right? And the other 4, which I wrote down over here, are actually 5 now. There's civil engineering, there's materials engineering, bioengineering, aero and astro, and the engineering systems division. Does anybody know the story of why it's called civil engineering? No civil engineers in here? Okay. Engineering was invented in the 1700s at École Polytechnique in France. And the word engineer comes from the French, ingénieur, which means to maker of war machines. Ta-da. What was the first engineering school in the United States? In 1797, if I got the date right. Right over here on the Hudson River. I was going to ask the Army guy. Which one of you is the Army guy? Yeah, okay. You didn't know that?
1802.
1802? Actually, I think it was, maybe Congress passed the law. Okay. They may have opened their doors in 1802, but I think 1797 may have been when Congress commissioned. And until 1844, 1845, the head of the commandant of West Point had to come from the Corps of Engineers. Okay? It was their engineering school. And in 1823, the second engineering school was produced in the United States in Troy, New York. Anybody know what's in Troy, New York? RPI, Rensselaer Polytechnic. You didn't graduate there, did you? No. Okay, anybody here can spell Rensselaer? Oh, who can spell Rensselaer? Oh, okay. Rensselaer, right? Not everybody can spell Rensselaer. Not even some of the people who go there. They call it RPI enough that, anyway. But in 1823, Rensselaer opened its doors. What was happening in New York State in 1823 that they needed engineers? The Erie Canal. And they needed people to design bridges, and they weren't breastworks, military breastworks, but they had to build canals, okay? And so they formed an engineering school, but to distinguish it from West Point, which was military engineering, they called it, their one course of study was called civil engineering, to distinguish it from military engineering. And that's how we got the name civil engineering. And then, arguably, MIT was the third engineering school in the country. Now, the University of Michigan claims that in the 1840s they had an engineering school, but I don't know if the students must have all been bears, okay? I don't know that there were, I don't know that many farmers or lumberjacks in Michigan were studying engineering. But anyway, MIT was the first school that broke engineering down into multiple disciplines. And what is course one at MIT? It's civil engineering, because that had already existed at RPI. What is number two? Come on, guys. Mechanical, right? What's number three in 1865? Nope, mining. Metallurgy did not enter the title until 1888. And materials did not enter the title until 1974. Okay? 4 was architecture. 5 was chemistry. And 6, I have no idea what it was, but whatever it was died, and it became electrical engineering in the 1890s. Why did we have electrical engineering in the 1890s? What two competitors were fighting for the electrical industry in the 1880s? Tesla? What did someone say? Okay. Westinghouse and Edison. And someone said GE. Who was the founder of General Electric? There were two founders. One was Thomas Edison, and the other was Elihu Thomson. Elihu Thomson spent 1 year as president of MIT. Thomas Edison had 400 patents, more patents than anybody else in the country at the time. Elihu Thomson had 380. He was number 2. And Elihu Thomson was a professor of electrical engineering at MIT. And the two of them formed General Electric right up here on the Lynn River. It's called the Lynn River Works for General Electric. It's the original plant of General Electric. So anyway, so electrical engineering didn't come around until the 1880s. Chemical engineering, where was that discovered? In the 1880s and 1890s. There was guys named Arthur D. Little and William Walker. You go over here, Walker Memorial, used to be the cafeteria and stuff. William Walker and Arthur D. Little. Anybody ever heard of Arthur D. Little? But he was the first management consultant. Oh, great. So we gave the world management consultancy. That's, well, with good comes the bad, right? Anyway, and what was the first school to have nuclear engineering in 1962? Come on.
Maybe yes to MIT.
Very good. Okay. Now, there are other types of engineering, but essentially, oh, and Aero and Astro, the first school to have not an astro department, but an aeronautics department was MIT about 1918. Okay. Bioengineering, we were very late getting into that. The Engineering Systems Division, we certainly weren't the first. But I'll tell you the secret. Some of you are going to think about ESD, right? The original name for that, which only survived one draft of the report, was the Division of Engineering Management. I know this quite well because I wrote the report. Okay. I also had a guy named Todd Magnani from the management school on the committee, and I knew that he would kill it because the Sloan School owns the M word at MIT. The engineering school is not allowed to use it. But it turns out if you went back to before 1950, there was a department of engineering management within the School of Engineering. And this guy, Alfred Sloan, who was Alfred Sloan?
The guy that makes all those pictures of that.
Yeah. But before that, he basically put together General Motors. He took Chevrolet and Buick and Pontiac and Cadillac, and he kind of grouped them together, and he basically showed how to manage a big automobile company, okay? And he was an MIT grad. And in around 1950, he gave a very large sum of money to MIT to essentially teach management. We had a department of engineering management at the time, and they took that department and they built a school. And what happens when you change the title of something? You build walls between the institutions, right? Big organizations, when they don't want people to talk to them, they give one of them a bigger title than someone else, and they won't talk to each other. And so management was removed from the engineering education in 1950 at MIT. And since then, if you read this report that formed this in 1996, it has a disclaimer at the bottom of the first page. I know because I wrote it. And it says, there's nothing new in this report that hasn't been reported in at least half a dozen studies of the last 20 years. Okay? What is different is if we don't do something about bringing management back into education, I didn't say it in those words, that we're going to lose our leadership in engineering education. Okay? So, anyway, that's what the Engineering Systems Division is supposed to be about. It turns out Doug Laufenberger was on the committee with me, and he saw this whole structure that we created as a way to create a division of bioengineering, which was easier to form than the Engineering Systems Division. And he formed the Division of Bioengineering, which after about 7 or 8 years became the Department of Bioengineering. And people don't realize that that actually was my vision, that by creating this parallel structure, or these perpendicular structures of departments and divisions, you would be able to kill departments and create new departments, which otherwise in the organizational structure of MIT and most other organizations, you can't get rid of anything, and it's hard to form new things because everybody knows once you form something new, you'll never get rid of it. Talk to the French, right? The French can't kill anything. Well, actually, they can. They can kill lots of people, but I mean, they can't kill anything that should be killed organizationally. Okay. Yeah. Anyway, so there are lots of different types of properties, which we'll talk about after we take a 10-minute break. How about that? On materials for this appendix for 21st century defense needs. You're going to have to read that eventually when you go through the material selection lectures. Probably, it may be for tomorrow. Another paper, which I'll go ahead and hand out now, I'll just let you pass it around, is The Future of Metals. Actually, give me one copy of that. Sorry. The history of this paper is, I was, around 1990, I was so sick of listening to people talk about fine ceramics and how they were going to make ceramic engines, okay? And I actually worked for the Office of Naval Research in Tokyo, Japan in the mid-80s, and they would have a ceramics conference at Shinjuku Station, and 2 million Japanese would come to this display of fine ceramics.
That's only like 4 square blocks of people then.
Yeah, so yeah, I know. It's actually just,
They huddle.
yeah. But the Japanese just thought ceramics were wonderful, and you got ceramic scissors and knives, and actually I have ceramic knives at home, and they work really well. They chip easily, okay? If they don't chip, okay? And they're a little pricey, but they work well. But the problem with a ceramic engine is when it breaks, it really breaks. It doesn't just wear out. It shatters. And so I used to go to some of these things, and with my personality, I just get up and tell people, well, actually, the thing I used to say is the only structural materials that have been made out of ceramics are Portland cement and toilet bowl, high volume materials made out of ceramics are Portland cement and toilet bowls, and I'd throw in the kitchen sink, but you have to line it with cast iron to give it fracture resistance, okay? If you dropped a pot in a toilet bowl, you're liable to crack it, okay? Well, I said this at conferences full of a bunch of ceramists, and they didn't take it well for some reason. But I never could figure these things out. That was part of my problem. But anyway, so I wrote this article, published in the Welding Journal because there was a society that would listen to me. But stole this plot from somebody, I can't even remember who, which is the volume of metals and which ones are used in what quantities in the world. So out of 100 pounds of metal produced in the world, 95 pounds are steel, okay? 2% is aluminum, 1.2% is copper, you got a little zinc, titanium, magnesium, tin, and titanium together is only 0.1%. So if you see that I spend a lot of time talking about steel, hopefully you'll come to understand there's a reason for that, and frankly, when you take the material selection lectures, you will come to understand that. People use materials for a host of reasons, which we're starting to talk about over here. Structural materials, we're interested in the mechanical properties, and in fact, one of the problems most people try to measure mechanical properties in terms of the force of fracture, but in fact you also have to worry about the energy of fracture. And when we get to selection of materials, I'll talk about that. You'll see that on some of the other videos. Force of fracture, how many pounds to break a bar in two. Energy of fracture, what happens when you hit it with a hammer and impact it, okay? And you'll learn that it turns out the US Navy was kind of the scientific leader after World War II because of the Liberty ships and figuring out why those Liberty ships broke in two, okay? And so a lot of our use of the science of fracture mechanics and the understanding of the energy requirements for mechanical design came out of a lot of work at the Naval Research Laboratory. In any case, so as I was thinking about this course, I'm supposed to be talking about structural materials. Most things you read about in the Wall Street Journal and Scientific America have nothing to do with structural materials. They have to do with fancy chemical, magnetic, electrical, optical, thermal, other types of properties. And in fact, you get all these different types of properties you can think of, and then you actually can start combining them. What's piezoelectric?
Crystal that makes voltage.
Right, you apply a force and you get electricity out. Or you apply electricity and you get a force out. That's sonar, guys. Piezoelectric crystals, okay? Superconductivity, zero resistance, only occurs at low temperatures. Magnetothermic, okay? Well, NIST has been working for 20 years on coming up with a more efficient refrigerator that uses magnetothermic materials. So use magnetic fields to generate cold, okay? Or, you know, a refrigerator is just a heat engine, so hot and cold using magnetism. Thermoelectric, well, anybody know what thermoelectric materials are used for? I just happen to have a thermoelectric material here somewhere. Here. Ta-ta. This is, I think, bismuth telluride, little rectangles in here with aluminum plasma sprayed between a polymer insulators. And so this will put out 5 volts of electricity if you put a temperature differential of like 20 degrees centigrade across it, okay? The bismuth telluride or lead telluride or whatever it is. It's a semiconductor material from 2,6 group. Will, in a temperature gradient, will give you 5 volts of energy. Well, They use this on pipelines in the middle of nowhere where you have no electricity to develop the sensors to tell you if you got flow in your pipeline or the temperature of what's going through your pipeline. So it's very reliable as long as you have a source of heat. Well, what's the source of heat? Well, if the pipeline's a gas pipeline, all you have to do is have a very fine platinum catalyst on one side that will oxidize some of the gas. It's like, we call this a Coleman lantern. You ever seen a Coleman gas lantern that has a little mantle? You know what the mantle is? You know, it's a little silk, silk bag. They don't make them anymore? They're all, yeah, well, I guess I ought to go buy. I actually probably have some in my garage somewhere because I have some of those old Coleman lanterns. But silk is interesting because it's got a lot of silica in it. When you heat this thing up, you actually form a little quartz bag, and it's platinized. It's got a little bit of platinum on it. It makes a platinum catalyst. Platinum catalysts are very good for oxidizing hydrocarbons. That's why we use them in catalytic converters, okay? This is not your typical ceramic catalytic converter. I could have brought one, a ceramic one, but they're heavier. This one's made out of a very, very fancy stainless steel. And they would platinize this and they would oxidize the exhaust. That's very lightweight, and they wanted to design that because most of your emissions problems are when you first start up the vehicle. The catalyst isn't working when the catalyst is cold. When you start up the vehicle, all your emissions are going right out the back until you heat up the catalyst and it starts working. Well, if you got a big thermal mass, it takes longer to heat up the catalyst. And so it might be 2 or 3 minutes of running your car where you're spewing out all kinds of pollutants. You'll pass the test at the shop if you've run your car for 10 or 15 minutes. But if you went in fresh and tried to pass that test, your catalytic converter is not working, you'll flunk the test on the state inspection.
In my car, it'll actually fail after only a few minutes. So
Oh, okay. What kind of car do you have?
that's an old BMW M3. Catalytic converter is very, very far back.
Oh, okay. So it cools off, you know.
Cools quickly.
Yep. Well, this one would cool quickly, but it also would heat quickly because it has much less thermal mass. Okay. But you have to use a fancy stainless steel to make it. And it's platinized. Well, you're looking at chemical properties with that, the platinum. You're looking at thermal properties, the small mass, so it can heat up quickly. Anyway, there's all kinds of different properties. That thermoelectric thing they use on anywhere where they need very reliable electricity typically for sensors. Okay, where you have you can't hook into the power grid easily. Okay, there's lots of defense applications for that. Anyway, so there's lots of these different types of properties. These get the high press because there's big value added in many cases. Very small amounts of materials in many cases, but lots of value added. But, you know, do you want to make $1 off 1,000,000 tons of material, $1 per pound off 1,000,000 tons of material, or do you want to make a penny or even $1 off 1,000,000 ounces of material? Okay? It's a big difference in what goes into the bank. So it turns out the big volume industries, this is part of the Future Metals paper, are the structural materials industries. I told you there's 2 billion tons of cement. There's 1 billion tons per year of steel. The steel industry is 5 to 10 times the semiconductor industry. You wouldn't get that impression by reading The Economist or the Wall Street Journal, would you? Okay? Well, that's why I wrote the article. But no one, most people didn't believe it, except people in the steel industry. They thought it was wonderful. Okay? But in fact, we know more about steel than we do about silicon because it's just a bigger industry. The Army did a big study once about 15 years ago when everybody was talking about, you know, titanium and aluminum armor and ceramic armor and all this stuff. And the Army did a study of what they would be buying the most of, what material they would be purchasing the most of over the next 25 years. And after spending a couple $1 million doing the study, they came up to the conclusion they would buy more steel than any other material. Duh, okay. I would have taken that contract for a couple $1 million. Would have taken about 10 minutes to write the paper. Okay. Anyway, let's just take steel and compare it on a dollars per mole to silicon. So if steel sells for $1,000 a ton approximately, these are all rough numbers, okay, that's $1 a kilo, and there's 7.9, you don't have to write all this down, grams per cubic centimeter, that's the density. There's 56 grams per mole, and this all tells you that the value of steel in a mole is about 1/10 of a pound, okay, 56 grams, not 450, but it's close to 1/10 of a pound. The value of a mole of steel is a nickel. Nickel per mole of atoms, okay? Silicon, on the other hand, if I'm talking about something that's 1 square centimeter, like that little Intel Pentium 5 chip I sent around, about a square centimeter, it may only be, let's just say it's 10 microns thick. It might be 100 microns thick, but who cares? And that says you could lay down a thin film that's only 10 microns and it would have all the functions you need. That means it's about 1/1000th of a cubic centimeter, which is about 10 to the minus 4 moles. Okay? And that thing is going to be worth at least $10, if not $100. So you end up with something like $100,000 per mole is what we're paying for silicon as a semiconductor. Okay? So now you can see why the people on Wall Street or the economists or whatever are so enamored with functional materials. You don't use very much of it, but it's got a high value. And I took it down to a value per mole. All you really need to know is these bottom line numbers, okay? And maybe they're off by a factor of 10, but who cares? We're talking about approximately a million-fold difference between the cost or the value, how society values a structural material compared to one of our more glamorous functional materials. Now, not all functional materials are as valuable per pound as silicon, but silicon's sort of a reasonable benchmark, right? And so that's why there's all this, what some people call glam tech. Okay, now one of the, a friend of mine, he wasn't always a friend of mine, when I first started as an assistant professor at MIT and he saw my name tag at a conference and said MIT, he decided to battle me for the next 5 or 10 years, okay? And we would go to Navy titanium conferences. This guy was Mr. Titanium in the country. His name is Jim Williams, and he had just started, when I started as an assistant professor here, he was starting as a professor at Carnegie Mellon University. And we were both kind of competing for Navy money in titanium. And this was just before the, what the Soviets call their titanium submarine. Well, not Typhoon, but there was one before that, the attack, the Alpha sub. I remember I was coming back from Europe and reading the International Herald Tribune when I read about the Alpha sub in 1980. Okay, and this was a real wake-up call for the U.S. Navy, that they had built a titanium sub before we had. Of course, they later found out in the next few years that it was noisy as could be. Even though it could go faster under the water than our destroyers could go on top of the water, it could dive deeper than the collapse depth of our depth charges. You didn't have any problem tracking it because it was very noisy. And within 3 to 4 years, you didn't have any problem tracking it because it didn't go out of the harbor because it had so many cracks that you couldn't dive it, okay? And it turns out part of that was the politics in the Soviet Union. The Naval Research Laboratory had identified some fracture problems with titanium that they hadn't solved. And I remember going to some of these conferences and they said, how did the Soviets solve this problem? And in a few years we learned they hadn't solved the problem. They just built the ship. Okay. So the Alpha subs didn't have a really very long lifetime. But anyway, so there's this huge difference in value. So then I did this little calculation of what I call processing rate. So you can pass this around, which are some of my notes on processing rate. And because they wanted me, when they said, oh, Tom, you gotta teach something broader than just welding. You gotta tell people about vapor deposition and casting and stuff. And we are gonna get to casting eventually here. But as I started to think about vapor deposition this spring and what I wanted to say, I decided I'd do a calculation because I couldn't think of any structural material that's made by vapor deposition. I can think of coatings that are put on structural materials. Vapor deposition is extremely important for functional materials. That's how we make silicon semiconductors. We chemically vapor deposit or physically vapor deposit layers on there, and then we have to planarize the surface. So many of the faculty in this department who are into functional materials would want someone to teach vapor deposition, but I'm supposed to be the structural guy. And frankly, I used to do vapor deposition when I did my thesis and worked in superconductivity, but I haven't done any vapor deposition for 30 years. So I was trying to think, well, what am I going to say about vapor deposition? I did learn enough about vapor deposition that I decided I could prove why we don't use vapor deposition to make structural materials. And it's not that complex. So the first thing you need to know is the Langmuir. Okay? There's this guy, Irving Langmuir, who worked at General Electric Research Labs about 100 years ago. And he was a pretty good scientist. He won the Nobel Prize for his study of surfaces. And he was interested in surfaces for lots of reasons. But for instance, he was interested in tungsten light bulbs and how the tungsten vaporized from the surface, because that's how the old tungsten light bulbs burned out. You basically had tungsten vaporizing away in from that hot filament, and the filament finally broke in two, just fractured in two, but it was a vaporization degradation, erosion by vaporization. So Langmuir did a lot of studies, fundamental scientific studies on vaporization. And we now have a term, a scientific term called the Langmuir, and it works out to about 10 to the minus 8 atmosphere seconds. And when you get to the joining portion of the course, which will be weeks from now, you're going to hear about the Langmuir when we talk about surface contamination and how you have to get rid of surface contamination before you bond something. Well, the Langmuir tells you from the kinetic theory of gases, we know that these little atoms are bouncing around in this room, and if we want to know how long it takes to form one monolayer of atoms on the surface of this table, assuming that every one of them sticks, that hits, it's 10 to the minus 8 seconds. 10 to the minus 8 atmosphere seconds. That's because this room is at 1 atmosphere. If I was at 10 to the minus 8 atmospheres, I would have a very difficult time breathing, but it would take 1 second to form a monolayer of gas. If I was in deep space at 10 to the minus 14 atmospheres, it would take 10 to the 6 seconds to form a monolayer of gas sticking on the surface of something. That's what we mean. Atmosphere seconds. Okay? Just how fast the atoms are bouncing around at approximately room temperature. Okay? There might be a factor of 3 in here, but when you're talking about 8 orders of magnitude, who cares? I'll let you have the factor of 3, whichever direction you want. Because there is also this sticking coefficient, which is not 100%. But in any case, if I'm going to vapor deposit something, if I had 1 atmosphere of cobalt vapor, okay, in a container. So it'd be the same density as the air here. That's a lot of cobalt vapor. And do you have anyone have any idea how much energy it would take to create a mole of cobalt vapor? Well, a lot. Yes, very good answer. But I actually, without having done all the calculations, it turns out there's something called the, if I can find my notes. Okay. There's something called Richard's rule. Well, actually, before I get to Richard's rule, let me give you, where'd you go? Here we go. From basic thermodynamics, we know that a crystal is a regular arrangement of atoms, and a liquid is an arrangement of atoms that's not quite as regular. And it turns out, in order to go from this crystalline form to this liquid form or glassy form structure, I have to break about 10% of the bonds. Here I have bonds in every direction. This is a two-dimensional crystal, but it's really 3 dimensions. But to go from a solid structure, crystalline structure, to a liquid structure, I have 10% fewer bonds because it's more open. Most things expand as a liquid because the bonds are breaking. You have more void space and stuff in between. To go to a gas, a vapor, you have to break all the bonds. And in fact, this is approximately correct because there's about 8 to 10 atomic distances between atoms at room temperature. Now, what's the easy way to calculate that? Does anyone know if I had a pound of water and I converted it to steam at room temperature, what the volume increase would be? You could go through the ideal gas law. You know, water is 1 gram per cubic centimeter. This would be a great problem set for an undergraduate. Converting units and doing PV is equal to RT and stuff, but I'm not going to do that to you. But does anybody have an idea about what the approximate volume change is? Or we don't have any Coast Guard folks this year, right? The volume change of methane when it goes from liquid methane, liquid natural gas, to gaseous methane at room temperature. So we're bringing in ships of LNG into Boston Harbor. And we have these ships that are 120,000 ton ships, right? 10 to the third, very good. It's around 600 or 800 for methane, but for water it's about 800, but I like 1,000. I can take the cube root of 1,000 more easily than I can the cube root of 800. Oh, the cube root of 800 is about 9. Cube root of 600 is about 8. But in any case, whether it's 600, 800, or 1,000, that means that the distance between atoms at room temperatures in the vapor phase is about 8 to 10 times, because they're in contact basically in the liquid and the solid phase. But if there's a 1,000-fold increase in volume when you vaporize them at room temperature, we're not talking high temperatures, but and it's 1,000, you take the cube root of that. You know why I'm taking the cube root, right? Okay, just talking about a volume. A density, it's about 1,000, okay? Well, it turns out we know from thermodynamics that's true because there's something called Richard's rule that you can get out of this is metallurgical thermodynamics, and it talks about Richard's rule that the heat of melting divided by the temperature of melting for the liquid going from the solid to the liquid is 8 to 16 joules per degree. And if you plot that for lots and lots of elements, the heat of fusion versus the melting temperature, you follow they see they're on this slope of about 8.4 joules per degree. That's Richard's rule. You have to break 10% of your bonds in order to go from solid to liquid. And then there's Troughton's rule, which is down here, somewhere it should say Troughton. Troughton's rule, that it's 10 times that. It's 88 joules, and here's Troughton's rule for vaporization, the heat of evaporation versus temperature, and a slope of 88, or here it seems like it's getting a little steeper slope, maybe it's 160, but whatever it is, it takes, you got to break 10 times as many bonds, because if you're talking a FCC crystal, face-centered cubic crystal, how many nearest neighbors does it have? 12. So to break all the bonds, I got to break 12 bonds. If it's a liquid, maybe I have to break 1.2 bonds, okay? So the heat of fusion is 1/10 the heat of vaporization. It takes a lot of energy to vaporize something. Now, if I had, let's just say I wanted to lay down some, what I say before, cobalt, whatever I said. I wanted to make a cobalt structural material. And cobalt's very expensive. I might need it for an aerospace thing. So $20,000 a pound, I can make this out of, I can afford to make a spacecraft by structural material by vapor deposition, right? Well, how long would it take at 1 atmosphere to lay down a monolayer? 10 to the minus 8 seconds. Or, you know, in 1 second, I'd lay down 10 to the 8th atoms. Well, that's about this thick in 1 second. Because if it's well, actually what I did here on the handout for you, the rest of this I calculated, or I show you in the rest of this what the molar volume for lots of different metals are, or materials. And you find that in general, just the atomic weight and the density, and you can look at the radius, the size of atoms doesn't vary a whole lot. You know, it's 1 or 2 angstrom radius, okay? But the molar volume is about 10 cubic centimeters per mole. Maybe 20, maybe 7, or 4.5, whatever it is, okay? Aluminum is exactly 10. But it's about 10 cubic centimeters per mole. And if I take, that means 1 cubic centimeter is 1/10 of a mole. 1/10 of a mole is 10 to the 22nd atoms. And the cube root of that is about 2 times 10 to the 7th. Well, that means that I can lay down a centimeter of material in about 1 second if I have 100% sticking coefficient in the Langmuir. So if I had 1 atmosphere of cobalt vapor, it would I could build it up a centimeter a second. And that sounds pretty good, except one of the problems with vapor deposition is it tends to lay down in everywhere. It's indiscriminate, right? The vaporization is caused by heat, and as Pauly said, heat is a disordered form of energy. And so not only does it lay down where I want it to lay down, it lays down all over the rest of my chamber. And so my chamber just, in no time, it fills itself up as a solid mass of cobalt, right? So it turns out vapor deposition processes tend to work at pressures of 10 to the minus 6 atmospheres or something. And it means that the actual production rate by vapor deposition on the back side here is a few microns to hundreds of microns per hour. It rarely goes above a millimeter per hour. Okay? Now, it's going to take 10 times the energy to vaporize the material. If it's a structural material, I got to use it in very large volumes, right? So I have a tremendous amount of energy to form the vapor, and then I'm going to grow it at most a millimeter an hour, maybe a 1/10 of a millimeter an hour. And I'm going to have to go in and clean 90% of my stuff off the rest of the chamber, because only about 10% of it gets onto the surface that I really want to use. It's depositing on the walls of the chamber and everything else, right? So does this sound practical to you for forming large volume structural materials? Now, I want to lay down 100 angstroms on a piece of silicon. you can start figuring that out, and it works out just fine for the economics of making something that has $100,000 per mole value. But when you start talking about something that has a 10 cents per mole value, it's a lot harder to justify vapor deposition. Okay? Yeah.
What's the advantage of vapor deposition if you were to use it for a structural material?
Well, since no one's really done it, it's not clear what the advantage would be, although one advantage is you probably could make glassy materials that potentially could be very pure if you spend even more on purifying, keeping everything very pure. If you make glassy materials, we know that some glassy materials, and I was looking for my met glass material, I must have thrown it out or something, I don't know, or loaned it to somebody else on the no return plan. But you can make sheets of glassy material that will be stronger than MP35N. Now it'll only be about 10 microns thick, but if you could vapor deposit that and you could make bulk materials, it could be stronger and more corrosion resistant. I mean, it'd be better than MP35N. Okay? So you could.
So are there people out there trying to make it better? Like say you were to lower the pressure a lot and you could just slow the process down and control it better.
Yep. Various people will seize on certain improvements. And so far as making glassy metals, we'll talk about this a little bit later, I guess next Monday. You know I'm not here the rest of this week, but I will be here next Monday. One way to make metals is rapid solidification. And back in the 1960s, a Professor Paul Duez at Caltech found that if he spread liquid metals, or in this case nickel and boron, on a very fastly spinning water-cooled copper disc, he could spin off foils, and the disc might be, the drum might be spinning at 60 miles an hour surface speed. He could spin off little thin foils, not much thicker than a piece of paper, that cooled at 1,000,000 degrees per second. And if you do that, you could keep the metal from crystallizing. It would end up with a glassy structure. And so all through the 1970s, when I started as an assistant professor, you wanted to get money in rapidly solidified powders or rapidly solidified metallurgy. There were hundreds of millions of dollars, if not billions of dollars, because this was going to be the new way, not from the vapor phase, but from the liquid phase. All you had to do was figure out how to consolidate those foils or those powders into a solid material. Well, how do we do that? Well, we do that by heating things up. Well, you heat them up, and all of a sudden, the atoms rearrange into a crystalline form. So a guy, Bill Johnson, one of Duez's students, who's now a professor at Caltech, he played around, and he got things where he could make what he called bulk metallic glasses. Okay? And bulk metallic glasses, he can cast things 2 or 3 millimeters thick, and they'll still have the glassy structure of a metal. And it has fantastic corrosion resistance, has fantastic strength, but you can't make anything an inch thick, but you can make it several millimeters thick, and so you could do a lot of structural things with 500 KSI strength and corrosion resistance and all this other stuff. Now, it can never get above about 300-400 degrees, or it will revert back to lousy properties, but so you can use it in the same temperature range as plastics. Okay. The only commercial product they ever came up with for the last 15 or 20 years was golf clubs. You can sell anything to a golfer, okay? Any new material you want, golfers will buy it. In fact, sports equipment is one of the leaders for new materials, uses of new materials, because you know, if you have no athletic skill, you can purchase it with a fancy material, right? That's the hope, right? Okay. So in any case, the only problem is people have learned that you get about 100 shots from the golf club, and then it starts to crack. So a few other problems with it, okay? Picking out a new material, designing a new material to have all the properties, fracture resistance, corrosion resistance, strength, ductility, it's not the easiest thing in the world. If it was easy, we'd all be doing it, okay? But anyway, does that answer your question? Bulk metallic glasses, okay? Pardon me? Yeah, well, it's unobtainium, but you know, look, the U.S. government spends billions of dollars on these things. You know, after rapidly solidified metals, it became fine ceramics. They were going to make ceramic engines, and after that, it became high-temperature superconductors. Okay, and then it became right after that. Anyway, not too long after that, it became nanotechnology, and nanotechnology has survived for 12, 15 years now. But you can do the same analysis that I just did for nanotech. And nanotech, if you're really talking nanotech, the particles are only 10 to 100 times greater than the atoms in size. And therefore, now if you cube that, that's 1,000 to 1,000,000 times more atoms per particle. But nonetheless, it turns out if you compare this to liquid phase processing, which is basically melting a liquid, which by the way takes how much energy compared to the forming a vapor per mole? 1/10 the energy. So it's fairly energy efficient to melt a material rather than vaporize it. And you can pour it into a mold. So you flow it into a mold. Viscosity is the parameter of choice. And it turns out you're going to find that your liquid phase processing is somewhere between 100,000 and 100 million times more efficient than vapor phase processing. And because structural materials are used in very large volumes as compared to often small volumes for functional materials, the reason we start with a liquid and cast virtually every structural material starts out as a casting. That's not always true of some of the ceramics, but most of them, all the metals, start out as a liquid. They don't go through the vapor phase route, partly because of the energy cost, okay? Partly because of the processing rate, okay? Partly because of all the cleanup you got to do, because vapor processing is sort of indiscriminate. It coats everything. Yep.
What if you were to make something like a drill bit
Yeah.
that would be able to machine MP35N?
Actually, MP35N is not that hard to machine. But anyway, it can. Okay, but they do. They titanium nitride coat drill bits. You can buy them at Home Depot, and they cost pennies more than a regular steel drill bit. It's a steel drill bit, but the surface has been coated, and that's a structural coating by vapor deposition, but it's not the overall drill bit. If you made a titanium nitride drill bit, the first time you drilled, you'd shatter it, okay? But as a thin film, it actually has very good wear resistance, which is what you're using it for. So that answer, I didn't even let you ask the question, but if you want, go ahead and ask the question.
That was it. I mean,
Okay.
technically, there would be structural applications for very small amounts.
Oh yeah, absolutely. In fact, somewhere, if not here, in some of my other notes, I point out that we do vapor deposit, maybe it's on the first page, we do vapor deposit things on structural materials. There's no question about it. Like titanium nitride on drill bits, like we put corrosion resistant coatings on. We do lots of vapor deposition, and someday I will add vapor deposition to this course. Maybe not this year, but maybe next year, about why we do it, but we're not doing it for the underlying thing that's going to support the load. We're going to do it for wear resistance or corrosion resistance or some other function. Okay.
Would you use that to make like surgical?
Well, surgical tweezers, if we're talking nano tweezers or something like that, yes, you could do it by vapor deposition. You may need to. But if you're talking about the old kind of blood and guts, you know, tweezers that you're going to pull a splinter out of somebody or a kidney stone or something, then you're still going to make that by liquid phase processing. Okay. So, yes.
You keep saying the problem, or one of the problems is cleanup and the indiscriminate deposition. It seems like a natural thing to mold, like almost like pipe, but why can't you use vapor deposition?
Vapor deposition, oh, you and then deform it?
So you mold it to an interior surface, like a reverse cat or a reverse mold.
Oh, okay.
The mold
Well, the Army's been trying to do that for gun barrels for years. They've been trying to put vapor deposited structural coatings on the inside of gun barrels because they have propellants that will wipe out the gun barrel after one shot. Very good propellants, but they not good on gun barrels. It's good if you're making gun barrels and selling them, but it's not good if you're the Army buying them. So they have, people do things like that, but that sort of limits the functional geometry of the parts you want to make. We like to make things in all kinds of shapes, right? So yeah, so you can think of things, and I just thought of an example, the Army and gun barrels, where you're trying to lay something down on the inside of the gun barrel. And the Army's developed all kinds of techniques over the last 100 years to try to vapor deposit. Well, first, right now, the big thing is chromium. They just electroplate chromium on the inside of a gun barrel. But they've tried all kinds of vapor deposition. They know there are better materials than chromium, but there's nothing as cheap, okay? So yes, you probably could do some of these things if we're talking aerospace. And if I thought real hard, I might even think of a vapor deposited structural aerospace material, okay? Or if I knew everything. I mean, there are probably some things out there. And you guys are going to go out in the real world and say, a few years, you're going to see something and said, Professor Eager was wrong, I found a vapor deposited structural material. But I'm going to, if you come back and tell me that I was an idiot and I didn't know about it, I'm going to say, what was the price, what was the function, you know, and I'm going to hold my ground and say, you're not going to make bridges out of it. You're not going to make Ford Tauruses out of it. You might make Indianapolis racers. You might make spacecraft. I mean, I can think of cases where they've made 2 millimeter thick diamond films, not just for the thermal properties, but for some structural properties. They make diamond windows in certain infrared devices, and it has to have structural properties. It also has to have certain optical properties that it will transmit the infrared, okay? But okay, there's an example. But they're not real big. They might be 1 or 2 inches in diameter, but you're not going to build a ship out of it. You're not going to build a car out of it. You could, but there's only a couple of people in the world who could afford to buy the product, okay? Remember, we're talking about imparting geometry and function at a reasonable cost, right? If we're talking structural materials, imparting geometry, mechanical properties, probably large volumes at a reasonable cost. And if you put all 3 of those together, I could find an example where you want to take any one of those, or maybe 2 of those, but you put all 3 of them together, you're restricted. And cost is the killer, okay? The Navy wanted to build an all-composite submarine after the Alpha Sub. And many people in the Navy says, well, they went up to the Hill and told Congress, we'll build a titanium submarine. And Congress said, no, we're not going to be second. And they took away from Admiral Firebaugh the $100 million design budget for the Seawolf in the mid-'80s. Congress zeroed it. And they gave the money to DARPA to design something beyond titanium, okay? Well, a bunch of admirals went up to the Hill and they said, oh, no. And so Congress gave back Captain Firebaugh his $100 million for design. They kept the $100 million for DARPA. I went to the workshop along with a bunch of other people in Reston, Virginia, and it was a 3-day workshop. And I think in some of the other videos, you'll hear the stories of that. But the composites guys came in and they just, you know, they must have been some of the people sitting in the Defense Department thinking about what you can do when you're not limited by science or physics, okay, or chemistry, okay? When you can just conceive of the inconceivable, okay? It's like the National Aerospace Plane. What a waste of money, okay? But anyway, these are the people who gave us things like Star Wars and a few other things. Not that some things didn't come out of those things, but some of them did, but not the product that they were selling. So there's processing rate, and we will actually get to some other things. Casting actually is the next thing. I didn't get to it today, but we will get to it. But it'll be on Monday. And tomorrow, I guess you're going to be here at 6:30 or 7:30, and you can watch the movies.